workshop, but couldn't make it here today. But we're happy that you could join anyway by Zoom. So looking forward to the talk.
All right. Thanks a lot, Henry. And indeed, my apologies for not being there in person. I had a lot of grand plans of flying specifically for this, but and managed to get trapped in Israel. So I'll basically be continuing where Peter took off in some regard. We'll kind of be bouncing back and forth a little bit. And it's my pleasure to talk to you a little bit more about these cryptographic correlations that Peter started talking about. And I'll be giving a couple different viewpoints of this, with a warning that I'll predominantly be focusing on things that, okay, so related to function secret sharing, which is an area of research that I've been a part of. Okay, so feel free to jump in if you have questions. If I don't hear you, please either be more aggressive, like jump up, wave your hands. I can see a tiny little picture of everybody. Happy about that. I was going to join the live streaming just to see what the room is, because sometimes they pop that up. But this is even better. Okay, excellent. So, good. Okay, so let me start by just a bit of a couple of high-level recollections from some of the material that Peter mentioned. So first of all, remember that one of the big distinctions of designing secure computation protocols depends on whether you have the assumption that there is an honest majority of the participants or not. Okay, so we will not be focusing all that much, unfortunately, on honest majority. Let me tell you, there's way too much material in secure computation stuff I'd love to talk hours and hours and hours about, and that's a threat. But we won't be doing much of that today. So, but in the honest majority case, one of the really kind of important or striking things there is that you can achieve information theoretic security. So you don't necessarily need any sort of computational assumptions. And there's different styles of techniques that are very useful in that regime. On the other hand, for dishonest majority, so if you don't have any sort of setup or any sort of starting point, then necessarily this requires public key cryptography, for example, oblivious transfer. But as Peter mentioned, one of the really useful ways of approaching these types of protocols is by this MPC with pre-processing setting. And one of the benefits there is that you can kind of push the necessary cryptography to an offline phase that's independent of the actual secret inputs of the parties. And this I'll be really focusing a lot more on. But that means that what you're left in is the online part. So once the parties actually learn the inputs, they want outputs quickly. This can be done much more quickly, more cheaply, and without any sort of cryptography. I'm not going to be formal about how that's defined, but there is a formal way of defining that. Okay, so this is partly a recap and partly a glimpse into your future of the Peter's next hour. So you saw already this top row of garbled circuits and linear secret sharing. And the benefit of these is that they're relatively lightweight comparatively the tools we're using in cryptography. The downside is that the communication complexity grows with the circuit size. This is sort of inherent. On the other hand, so in Peter's next talk, he'll go into some more of these newfangled, heavier duty cryptographic tools that of fully homomorphic encryption and homomorphic secret sharing. And this gives some kind of trade-off at a very high level idea, where the benefit is now the communication complexity can go sublinearly in the circuit size. So this was kind of an exciting thing. But the downside is that in order to do so, the types of cryptographic tools tend to be heavier. Okay, what I kind of want to focus on in this talk is a little bit of somewhere in between these two row worlds, where I'm going to be talking about cases where simpler instances of the bottom row, so in fact, I'll give a couple examples of somewhat like a weak version of somewhat homomorphic encryption and also homomorphic secret sharing for very kind of simple function classes, can actually help give back to efficiency improvements in the upper row of these classical approaches. And that seems like, in terms of the state of the art, kind of this combination of weak versions of the lower plus the classical frameworks seem to give the most efficient protocols in a lot of different settings. Okay, so indeed, we will be focusing on secure computation with pre-processing. So here they're split into the offline, online phase. The offline is independent of the inputs, so the inputs X and Y only come on later in the game. And then, as we've mentioned, there's a lot of motivations for doing so. In a little bit more detail, so the fact that here are these correlations, this represented by the purple and green here, this is sort of the result of pre-processing. For now, you can either think that somebody gives this to you, or pre-processing it itself is a different sub-protocol to generate the correlation. Okay, but however they're generated, they're independent of the party's inputs. That means that whatever this process is can be done offline cycles. You know, you think about the middle of the night, I don't know, you're running something, it doesn't need to be exactly on spot. I mentioned this already, that this allows you to push the necessary kind of heavy cryptographic part to the offline. And also the fact that if we're going to look at a lot of examples, that the type of pre-processing that you generate tends to have a lot of nice properties. For example, if I want to be able to do arbitrary sorts of Boolean or arithmetic circuits, there's a very simple, very structured copies of the same sort of correlation. In fact, we even saw these beaver multiplication triples, for example, that can allow you to kind of support any sort of online circuit topology. And so the fact that you have, it's beyond just kind of pushing the work to a different time period, but there's actually hope of being able to be more efficient in generating these things because they have useful, nice structure. And we'll see some examples of that. Okay, so indeed, in this talk, I'm going to have two main parts. And the first is these are sort of semi-orthogonal. Obviously, they're related to each other quite a bit, but two different questions that you can ask. So the first is, okay, what types of correlations are useful? What is it that is the goal? What is it that we want to be able to generate? And how are they useful? That is, like, what do they give you in terms of online secure computation protocols? And the other question is, great, so we have a target in mind. Now, how do you actually generate these correlations? So we're not just pushing the problem completely, but we're going to actually address that question as well. Okay, so let's start with the first part. And I'm in luck because Peter actually already gave you a lot of different examples of these types of correlations. Okay, so these are really from things that each appeared in his slides that you saw. Don't worry if you don't remember exactly what they are. But for example, even going, by the way, to the honest majority setting, which I've been focusing mostly on dishonest majority for the correlated randomness, or this MPC with pre-processing, because it's sort of necessary to pull the heavy cryptography out from the online. But even in the honest majority setting, you still get a lot of efficiency speedups by considering this pre-processing type model. Some that are come up all the time. So these beaver or multiplication triples, these are secret shares of random values AB in their product. Whenever I say shares, I mean just additive secret shares, either across two parties or however many parties you're talking about. An authenticated version of these, this is what is used in the speeds line of protocols for getting malicious security by using these homomorphic maps. Peter also showed you that. And also this one-time truth table correlation. Okay, let me throw some more useful correlations at you. Partly with the intention that you at least kind of, if you start hearing some of these phrases, a lot of these things get bounced around as terminology. This can also hopefully serve as some sort of lookup table if you see things in the future. But actually before then, okay, this is a different order than I was thinking. Just to kind of remind you, so how are these used? Okay, so this is exactly the protocol. So I'm going to do it just very quickly. So remember, what is this one-time truth table correlation? First of all, what you do is you think of whatever function you want to compute as a general truth table. Okay, I'm thinking about this as a two-party functionality. So this is why I've got sort of the party one's input on one dimension, party two's input in the other dimension. You choose a random cyclic offset R and S, and you rotate the table in each dimension, R in one dimension, S in the other dimension. This is what I call the permuted truth table. It's not actually like a shuffle or permutation. It's really just cyclically shifting in each of these dimensions. Okay, then you additively secret share that into two different matrices like this. So MA is just totally random and MB is set as it needs to be. Okay, so this is the description of the correlation, where here either parties get the secret share as well as the shifts. Okay, and there's a purpose why I'm rehashing this, just because I want you to first of all kind of see it's a common framework, and then I really am going to abstract this as a common framework in a little bit. Okay, so what is this first message? Don't even worry about the details. The point is music. It's going to send. I want to kind of communicate my input, but I cannot communicate my input. So I'm going to use part of the correlation as a mask. And instead, I'm going to send you the masked input. So now we both agree on the masked input, my masked input. Okay. You do the same. You send your masked input. Now we both know each of our masked inputs. They're protected because of the mask. And now, as a function of that, we can use our correlation, in particular, just looking up. So I have my table. I just look up in position U in V, some value, and output that. And you output so that's kind of, this is my part, and this is your part. And this gives us an additive secret sharing of what the output computation is. Okay, so this like masked inputs being revealed and then generating secret shares, in this case, of the output. Okay, so now I'm going to throw more correlations at you. It would have been slightly better in the opposite order, but this is what we've got. Okay, so yeah, I'm going to do this. Okay, so I'll just mention, I think I don't even really want to go too deep in what these are, but for example, oblivious transfer as a correlation. So Peter talked about oblivious transfer as a protocol that you use, for example, for either for GMW, if you're not using Beaver triples, or for Yau's garbled circuits for exchanging the inputs at the beginning. Okay, so that's a real protocol with real inputs that we're doing for OT. But you can consider a correlation version of this, which is essentially with random inputs. So the sender here is getting two random messages, or maybe n instances of this thing, and the receiver is getting a random choice bit and the corresponding message. And it turns out if you have a random sort of instance of this OT correlation, then you can achieve chosen input OTs very cheaply in a similar sort of version that I kind of use a masked value and continue from there. Okay, and more generally, if you have, say, in n instances of these OT correlations, this gives you a way of doing two-party secret computation of Boolean circuits with low communication. So, for example, just you have these like two instances of OT plus 4 communication bits per AND. Let me just kind of mention this. I'm aware, and I'm sorry if I'm talking a bit quickly, but I always tend to go over time just because I get really excited about telling people about things. So let me not belabor these points too much. I will leave this in the slides and make the slides available so you have this if you want as a lookup table. Maybe just a couple mentions. So this OLE is very related to multiplication triples, as you've seen. Slightly different version where kind of one party knows one of the values. I won't get into it. The vector OLE is a version where, so one party has, you think about a vector A, another party gets a scalar X, and then we get additive secret shares of A times X. So here I have some random B and you get AX plus B. Okay, and so each of these things, maybe the important takeaway, even if not the specific choices of what these correlations actually are, is kind of the trade-off. So there's some correlation. This is being described as a way of sampling from a joint distribution. And for each of these different correlations, that gives us, we know how to get something useful from the NPC setting. And it kind of corresponds similarly, as you might expect, to what the correlations are. So for example, these vector OLEs are useful for doing secure two-party computation of chosen scalar vector products, which end up appearing in a lot of other sub-applications like zero knowledge. You saw already authenticated multiplication triples. So I'm giving your two mentions here that these. So the previous slide is all useful for semi-honest protocols. Like you want to do secure computation against semi-honest or passively corrupted party. These two examples are useful for boosting to malicious security. So you even saw exactly what was the basic transformation. This is speed, what speeds uses to go from semi-honest to malicious security. And I was happy to see there were a lot of questions about this fully linear IOP stuff. Um, I'm very happy to answer questions about that afterward. Um, that's a line of work that I'm certainly a part of. Um, and one mentioned that didn't quite come up in the last talk, but there's actually a version. So FLIOPs, these are useful. They can be useful both in the honest majority setting and actually also in the dishonest majority setting with preprocessing. So what is the correlation itself? That would take a significant time to really explain. Let me perhaps suggestively call them some kind of compressed one-time paths for proofs, which I think even as a co-author on this thing doesn't give a whole lot of information. But something that's very cool about this correlation, I think, is that so if you kind of it's a way of taking a beaver multiplication. So if you start basically it starts with the same semi-honest protocol as speeds, where you're using it's what Peter described as the GMW protocol using these multiplication triples. So both start with the same basis, and then the compilation to malicious security is quite different. Speeds has a if once you're given this correlation, it's very cheap, very easy to do the check. But in some cases, this correlation is very large. So for example, as Peter mentioned, if my circuit is a Boolean circuit, well, I can't actually have my, here what is alpha? Alpha is this authentication key that's, so the correlation itself is a bunch of these like semi-honest multiplication triples, and then each of those scaled by some MAC key. So if my circuit, for example, is over bits, I can't have, so these are secret over bits, the first part, but these are must necessarily be secret over a much larger space, like a statistical security parameter. Otherwise, you're not getting any security from a MAC key if the MAC key is only 2 bit, 1 bit or 2 bit. So the correlation size here ends up being quite large. And here, something that's kind of cool is that the correlation has the semi-honest triples and then something that scales sublinearly and in fact even logarithmic in the size of the circuit for kind of the extra needed to get to malicious security. So that I'm not going to talk about at all anymore in this talk, but feel free to ask me questions about that. Okay, and another useful class, this is sort of a more of an abstraction or a generalization of things, is the class of additive correlations, which are simply described as all of the possible correlations that you can express by defining, so kind of specifying a central distribution. And then what the parties get, what the actual correlation is just additive signatures of a sample from that distribution. So for example, here what I've written up here is exactly an instance of that. Where what is, and in fact, I've even kind of described here in that format where the brackets mean additive secret shares of this. So here, my capital R is this without the brackets, and the correlation itself is the brackets in the sense that we're doing this additive secret sharing. Okay. Okay, so now take a little breather, take a step back. You've seen a lot of different examples of useful correlations. And now I want to ask the question, what's in common with everything? Um, and for now, let's even kind of simplify things. Let's just focus on passive security. Forget about these more complicated ones of getting malicious security. How can you try to design something or come up with a new type of correlation that could help, or try to understand given a correlation if it's useful or not? And I would say that at least to me, when I was approaching this area the first time, it seems like I didn't really have a good answer to that question, in the sense that it's a lot of, here are some examples that we found are very useful. And these examples are indeed very useful, but trying to kind of generalize was not obvious. And what I'd like to present to you is some way that doesn't capture everything, but it captures, I think, a lot, or maybe even being so bold as to say most of the types of useful correlations, with a perspective, using a tool called function secret sharing, and I'll tell you about what that is. Okay, but so kind of what is the setting? What am I thinking about here? So suppose that if for example we just want to do secure computation of arithmetic circuits, so ones with addition gates and multiplication gates over some ring structure, let's say, then we have pretty good answers. These multiplication triples are really good for handling multiplication gates, and addition or linear gates you can just do on secret sharing. Okay, but say I want more. I want more generalization, and I want to be able to express my circuit with chunkier gates instead of taking everything and decomposing it all the way down to just additions and multiplications. I want to be able to consider things with maybe mixed types of domains, with other more complex gates, useful nonlinear gates, things like I have two inputs to the gate and it outputs, maybe I have two inputs that are over some large field, okay? I've just done some multiplications over a field, and now I want to do something like an inequality check. Are these the same things? Um, and for those of you who have seen a bit about secure computation, this this kind of concept of going back and forth. So even kind of in the original slide with the cross at the beginning, and there's the Gauss-garbled circuits, and there's computation with, say, linear secret sharing. Gauss-garbled circuits are fantastic for Boolean circuits. These linear secret sharing approaches are very good for arithmetic type of circuits, where, for example, a multiplication over some large field, I don't have to decompose as bitwise computations, but instead I can just treat this already as a multiplication over the field. But if you want to do both, if I want to do both these, arithmetic structured computations and then do, say, a bit decomposition, or then I want to do exactly like an equality check between two field elements, this is something that described as an arithmetic computation is extremely high degree. It's very expensive if you just stay in that regime, and also expensive if you have to do bit decomposition of everything. So there's a lot of motivation and a lot of work in practical MPC trying to be able to kind of do mix and match of different sites, different types of circuit domains. Okay, so let's say this is a goal. And the question is, what types of correlations can help to do secure computation of circuits of this kind? Okay, what I'm going to describe is a general framework that essentially takes a circuit and something called a function secret sharing scheme on related function classes. Now hold off on that. I'll tell you what that is in the next slide. But basically using some tool spits out a specification of, first of all, a distribution on correlated randomness and a corresponding protocol that allows you to do secure computation where the cost scales essentially, so the online communication cost scales with really all the wires. So for example, if this is some maybe bit decomposition gate, I've got some my circuit in my slide circuits go down. Okay, that's a point of contention in different groups. But say my circuit is going down. Okay, I've got some wire in this circuit that has maybe a large field element that's being carried here. And I want to decompose this into a bunch of Z2 elements of bits, the bit representation of this, and then operate on some of the bits of this thing. Okay, so in this framework, I'll end up giving as part of this gate will correspond to some extra amount of correlation that will be given, such that now when you reach the online period, we're going to have to communicate something, basically a masked input value for this wire. And then just for the output values that you're going to use. Okay, so I'm not communicating it all for this inside portion. This is going to be something that you're going to do without communication. And this is how are we going to do that? Well, it's whatever this tool FSS is. Okay, so I like this both because at least it was very satisfying to us as the co-authors of this work, that it gave some framework that explained, in fact, a lot of existing different types of correlations that at face value seemed like they were a little bit unrelated. In fact, to this day, whenever I have to come up with the expression of how to use a Beaver multiplication triple, the fastest way in my mind is to translate to a function secret sharing interpretation and then spit it out. But beyond that, actually, we were able to show that using this framework and existing constructions of function secret sharing, this object for simple sorts of function classes, gave us new approaches for useful correlated randomness and corresponding protocols. So in this work, we have a couple different ways of doing this. One, and this, when I say circuit dependent versus circuit independent, I'm talking about the correlation themselves. So here, for example, there is some circuit that I want to securely compute. Certainly, I need to know kind of how many of each type of gate there are, because that for each of those, I'm going to need to add some amount of correlation. But the structure of how these things come together, if I'm allowing my correlation to depend on that, then it's called a circuit dependent correlation. And if not, if I just say, okay, you tell me how many bit decomposition gates, how many multiplication gates over this ring, then, but not how they connect with each other, then I can tell you the correlation. This is what's called circuit independent. And certainly circuit independent correlations in general are better. But sometimes they have a little bit more overhead to get this independence. So for today, I want to give you a high-level idea, and I'm going to keep it as simple as I possibly can. So I'm only going to talk about the version that is allowed to depend on the circuit. But there's a way in this approach that you can get rid of that. And just as a quick mention, so things like Beaver multiplication triples are circuit independent, right? They only need to tell you how many multiplication gates do you need to securely compute, but nothing about what the circuit actually looks like, how these are connected to each other. Okay, so to do this, I need to tell you about this tool, function secret sharing. And to do so, let me first start by quickly recapping what we all know and love of additive secret sharing. So here, I'm thinking about the secret as some group element. This is some single value, okay? And as you know, additive secret sharing splits this into two different group elements that add to what you want, with the secrecy and reconstruction properties as written. Okay, so function secret sharing is an analog of this, but where instead of just having a single group element, what you have, the secret itself, is a description of a function. Okay, so in a similar way, I want to be able to split this function into two parts, which each of them itself will be interpreted as a function, f0 and f1. I want that each one individually hides the original. Here, to be a little bit more concrete, we'll say that we have a function secret sharing scheme for some class of functions f, if that supports secret sharing for any class, any function within this class, and that the hiding is also up to knowledge of what this class is. So for example, if I tell you this is going to be a secret degree 2 function, you'll know that it's degree 2, you just won't know what the actual degree 2 function is. Okay, and what's the functionality here? So once each of us has our f sub I or f sub b, our shares of f, if any public input x comes along, so x is coming from the domain space of the original function f, then there's some way of us to locally evaluate our shares to get these output. Each of these is now, this y0 and y1 lie in the output space of the function f. And the correctness property is going to be that if I add together what each of us has generated, this gives us exactly an additive secreture of f of x. Okay. So you can of course think about effectively like f in some sense is some succinct representation of a lot of different values if you think about expanding up the entire truth table of f. And of course, one way to do function secret sharing is to just interpret, like translate f to its truth table and then symbol by symbol do an additive secret sharing. That's actually a perfectly legal FSS scheme, that's fine. But a lot of the time we're interested in the case where the size of these shares f0 and f1 is comparable to whatever the original representation size was of f. So if you have a succinct representation of f, I prefer not to expand this out to shares that are the size of the truth table. So in the next lecture, Peter will talk about FHE, fully homomorphic encryption, and also homomorphic secret sharing. Homomorphic secret sharing is very, very related to this, but it's the dual. Essentially, you kind of swapping the position of the function and the input, but I'll let him talk about that. Okay, so here's the framework. Step 1, choose your circuit. Okay, great. Here's my circuit. So in each of these, note that that each wire is associated with some group. I'm going to call it, G sub W for the wire. For example, maybe these are, as I mentioned before, maybe these are ring elements, and I want to do a comparison test. Are these equal or not? Or is one bigger than the other? Maybe this is a bit decomposition, so these are now, F2 elements, so forth. Each wire has some data type. Okay, and each gate is some function from the input to the output. And here, by the way, if I have some kind of multiple outputs, I can just, I'm still going to describe this as a single group, but you can view this as like a product group of whatever, so this is like F2 to the whatever the output length is. Okay, but here this superscript is just because I have too many subscripts. This is just some input group and output group for the gate G. Okay. Okay, so what I'm going to describe to you is a little bit of a combination of how we're going to define the correlation, sort of in combination with how is it going to be used, because that's going to motivate actually how to define the correlation. So the first part of what is in the correlation is that for each wire, we're going to sample a random mask. Okay, so for example, R1, R2, so forth. Okay. And the goal is that when we're actually in the online part of the protocol, the parties are going to step by step learn the masked values of each of these wires. Okay, so there's some secret inputs. If you had the inputs in the clear, you could compute this entire circuit, and in each wire you would learn what was the value on that wire. And instead, what the parties are going to learn is that value masked by the corresponding mask R sub W. Okay, and notationally, I'm going to call the masked value on wire W with a hat.
I have a question. So
yes,
you mentioned it, but I got a little confused. So you're thinking of every wire may have a different group associated with it?
Yes.
Okay, so it's because you mentioned something about if they have many output wires, you can think of it all like as a product group, but actually you're thinking of each wire alone as a group.
Yeah. Sorry, this is a little bit of like a detailed point that just in terms of having a nice notation that every single gate has like one input, one output, but what I'm trying to say is that can be interpreted as lots of different outputs, but there's some group that represents.
Okay.
Thanks. Yeah, feel free, more questions if you want. Okay, great. So really kind of specifying the correlation. So far I'm kind of describing this on behalf of a dealer. So suppose that there's a dealer. The dealer does not know what any of the real inputs are, right? This whole description of the correlation has to be input dependent. But the dealer does know the circuit. Again, because I'm considering the circuit dependent version to begin with. And the dealer has just chosen each of these masks for all the wires. Okay, so for each input wire that's owned by a particular party, so this party's input is supposed to come in here, he can just give the mask to that party. Okay. Sorry, so the R, like the corresponding RW for the input wire is given in the correlation, and the party can, I'm talking about now a combination of the online protocol as well. So the party has the mask, they have their input, so they can send out the mask input to everybody. Okay. So now that's how we get started with the protocol. And now we can assume we're somewhere in the circuit and we know the masked value of the wire. Again, kind of starting, we have that with the very input gates. And I'm going to show you how to preserve that at any point in the circuit across another gate. Okay, great. So now say that we've got to another gate. Here, this function right here. And as of now, we don't really have a way of going past this gate. I haven't told you the rest of what this correlation is going to be. But let's take a look at what we've got. Okay, so we all know the masked input. Okay, and what we want to learn, we all want to learn the masked output. Okay, so now kind of think about this computation. One way of expressing how you compute the masked output is by computing this public function. This is whatever the gate is, whether it be multiplication or bit decomposition or whatever. I don't want to compute it on the masked input. I want to compute it on the masked input minus the mask. That's the true payload. Nobody knows what that is. We're keeping it so that we only know the mask value. Nobody knows the true value. But what I'd like to compute is exactly this expression here. Okay. Good. So this is kind of copied over exactly the same expression. And let's zoom in here. Now remember that F sub G is public. This is something I'm assuming that everybody knows the circuit we're trying to securely compute, so that's not a problem. Also, X hat is the public mask input, but the parts in red are secret, and they have to stay secret. I can't tell you R in or R out because that will reveal if I'm assuming that you're going to learn the masked value. So if I also tell you the mask, that's revealing too much information. Okay. So I'm going to give this notation. This is like parameterized by two secret offsets, this FG with the superscript. And you can think of this as an entire function family, okay? Where each function is specified by a different choice, like some choice of the input mask and some choice of the output mask, okay? This is the function family I want to do a function secret sharing of. Okay, so suppose that we have a function secret sharing scheme for exactly this offset function family. Okay, so what does that look like? Remember, I'm kind of taking my function secret sharing scheme and now turning it on its side. So this is the secret function. Who does this secret sharing? Well, I'm just describing, think about a dealer is doing this. I'm just describing what is the correlation. Okay, so the dealer has sampled these masks. He knows what they are and can do this function secret sharing. And these are going to be part of the correlation I'm going to give the parties in order to do the secure computation of this gate, this F sub G gate. Okay, so again, so now a public input to this function comes along. That's this masked X hat in. We can both take our FSS shares, locally evaluate some output share, Y0, Y1. And the correctness guarantee of function secret sharing is that these two values add exactly to whatever my original secret function was at this input. And if you plug in, again, what was that? Okay, that's this mask input with these offsets. And this is exactly the mask output. Okay, why? So if I didn't have this R out, if I just had this is exactly the output, the plain text output of the gate. And this is adding on the output mask to that. Okay, so this is now essentially giving away that if I have So basically, if I have a function secret sharing scheme for the corresponding this offset function family, then I can use those FSS shares as a correlation, generate those ahead of time to allow you to go from masked input to masked output across that function gate. Okay, and I see that I'm clearly running over my time here. So let me skip a lot about how this can be instantiated. But I just want to mention briefly that in fact, a lot of the correlations you saw in the big list in previous slides can already be cast in this fashion. So let me just describe one instance. Remember, I said that you can always get function secret sharing by just secret sharing the truth table, okay? So now think about what is, if I'm using that secret sharing scheme on the offset function family, that's like taking my F and cyclically shifting the inputs to this function, the truth table of this function, and additively secret sharing that. This is exactly recreating one-time truth tables. Okay, and these are useful and not only as a very clean and nice way of explaining secure computation to undergrads, but also for a lot of practical applications where the function that there's, for example, you want to compute some large function and there's some chunk there that's very expensive to describe maybe as a Boolean circuit or in another way, but I can describe it as a relatively small truth table. So for example, Tiny Table showed how to do this with AES, where the S box itself was just represented as a truth table. I won't get into it, but for example, multiplication triples, these Beaver triples, exactly are a function secret sharing scheme of low degree polynomials. Which low degree polynomial? The one that multiplies two inputs, and now I'm taking those inputs and subtracting off these masks. So a way that you can do FSS for low degree polynomials is taking the secret coefficients and giving additive secret shares of that. I'll let you think about how that suffices. Okay, there's a lot of other extensions. So for example, if I want to do degree D maps, bilinear map, degree D gates, bilinear maps, there's ways of doing that just even with information theoretic secure function secret sharing. But maybe even more interesting is that we have FSS constructions from one-way functions that allow us to do other types of classes of functions for very cheap. So I don't have time to get into that either. But let me just maybe give you a quick example. So a useful such function family class is point functions, which evaluate to zero everywhere except for a single position. And let me tell you that for example, so exactly a point function that's non-zero in a secret position can give you exactly, say, like a zero test gate. This is FSS for a zero test type of functionality. So then I'm zooming through that a little bit. But let me close this part just by giving a couple more examples. So things like comparison gates, sign gates of larger spaces, bit decomposition, fixed point arithmetic, a lot of other things. So splines. This approach, by the way, has been picked up by other groups. This is not by any means a complete list of citations, and a lot of really interesting things for secure computation of neural networks, because this really has a combination of a linear layer together with a nonlinear layer, these activation functions. So a lot of really cool stuff that's being adopted in other spots. Okay, so I want to tell you not only just about what types of correlations are quite useful, but also to give you an idea of how to generate useful correlations. Okay, and I am going to definitely have to trim my material. So let me just very, very quickly tell you how a weak form of homomorphic encryption can allow you to generate multiplication triples, like these Beaver multiplication triples. And instead of even formalizing it, so suppose that you have some kind of the following object. So homomorphic encryption in the sense that you can, there's a key generation, you can encrypt the homomorphism. I'm just going to assume that you are allowed to do one multiplication. So I can take two different ciphertexts and multiply them, but that's all that you can really do. You can't do higher degrees, for example. And suppose that you have a threshold version of this, in the sense that when I'm generating, I have some public key that everybody is going to be using, and different people will have secret shares of the secret key, so additive shares of the secret key. Where as a distributed decryption protocol, there's some way that everybody can take their share of the secret key and in a common ciphertext and get some piece, some share of the plain text. Okay. So then the basic protocol for generating, remember, this is the goal is to get secret shares of random A, secret shares of random B, and secret shares of their product. So this maybe already is kind of cluing you into I want one multiplication. Okay. So everybody is just going to choose three random values here. This is not the final value. This is just a random value here. And broadcasts additive, like sends out the additive secrets, or sorry, these are encryptions in this notation. This is encryptions of your AI, your BI, and your CI client. Okay, now we're going to define the values. So A, B, and A times B are the values we're going to want to get additive secret shares of. So A is going to be defined basically as the sum of everybody's contribution AI, same with B. Now C prime here is still just random and unrelated to A and B as of right now. Okay, but I do have the property that each of these is random. Okay, and now here's kind of the interesting part. So by taking, I have now these two ciphertexts, A and B. If I have a way of multiplying the ciphertext, I can then subtract out, the ciphertext of this random thing. This gives me a new ciphertext. And we can do distributed decryption of this new ciphertext. And this will effectively give us, so what everybody has now, everybody knows their share AI of A. They know already their share BI of B. Okay, that's what these two parts. And now their share of this third part, which is going to be A times B, will be so this value here plus their delta. Okay, so yeah, sorry if I'm zooming through this, but kind of the important part is that by allowing this weak form, it's not going to be super strong homomorphic encryption of all sorts of circuits. By just allowing a single multiplication, you can already leverage and get useful correlations for in this case Beaver multiplication triples. Okay. And there's a way of getting active security on top of that, which I'm not going to get into. Okay, so before I'm forced to kind of close up here, there's one more main point that I want to tell you about. So kind of where do we stand? As it stands in some sense, we kind of have succeeded in pushing a lot of work to the pre-processing. But now this is the expensive part. And we haven't really gotten rid of the work per se, a little bit in the sense that we are leveraging, useful comment structure, for example, in the previous protocol I just described. But we can hope for a lot more. Okay, and note in particular that a lot of useful cryptographic correlations are very large. So for example, multiplication triples or any of these things, I need the correlation size to scale with the entire size of the circuit that we're going to compute. I need another instance of a multiplication triple for every multiplication gate. Okay, and this is something that seems like maybe it's not necessary. Okay, and just to kind of give you a thought, okay, well, remember, for example, suppose a very simple case study, the secure action that I want to do is just say perfectly secure communication. Well, we know how to do this with large one-time pads, but indeed they have to be very large. If I want true perfect security for a one-time pad, they have to be true randomness, which scales with the entire communication size. But this is not what people actually use. What do they use? Well, I don't really need true randomness. I believe that people are computationally bounded. So it suffices in my mind to have something that is as secure against computationally bounded adversary. And in that case, instead of using true randomness, I could compress this on both sides using a PRG. Okay, some flavor of this is really what's used for symmetric key cryptography or these stream ciphers. Okay, so this is great. What about for other types of correlations? What about secure computation? Okay, maybe for example, I have tons of multiplication triples, but note that these triples don't depend, they're random. Okay, random A, random B, their product. Another totally random CD and their product. And in fact, I'm okay with backing off with, instead of these being truly random, with them being pseudo-random. And in that case, is there some way that we can compress pseudo-random instances of other cryptographic correlations in a similar way? And this is a notion we put forth a few years back called pseudo-random correlation generators. And that's exactly what it is, where kind of the analog of PRGs, these are PCGs, C for correlation. Okay, so what are the properties that they want? So the thing itself, a PCG is defined by both a distribution over short seeds and some sort of local expansion procedure, okay? Such that, first of all, when you sample from the distribution and you expand out, of course, I want that the long outputs are distributed with respect to whatever my eventual target correlation was. This is represented here by x0, x1, looking computationally like a sample from the target distribution D. But something even stronger that you have to keep in mind is that I want kind of the security. In order for this to be meaningful, I need it to be the case that you even have some kind of insider security, in the sense that if I have one of these seeds, this seed should not give me any further information about your expanded input than, of course, what I could already conclude from my expanded input. Okay, and this is kind of combined the notion of these PCGs. Okay, so of course, we're kind of additionally pushing the problem to another question. So where do these seeds come from, right? Well, this is now just a new correlation, but we've made a lot of good progress here. So the small seeds themselves either need to be given via a third party or a dealer or via some other secure computation. But note that we have reduced the problem here. Instead of generating these large things, which in general are truly random or something in the communication complexity of these protocols, even of the one using even using somewhat homomorphic encryption, scaled with the size of the output, the entire long correlation size. And typically, using these PCG constructions, you can reduce this now to a much lower communication complexity, computation complexity. And in fact, even as an additional bonus, which I haven't really talked much about, but as an aside, that you can, because now the computation you're doing like this much smaller scale secure computation. If you want to have a correlation generation against malicious adversaries, now you can kind of put the overhead on this small computation instead of something that's scaling very large with the correlation size. Okay, so let me summarize just a little bit of the state of the art. I might go over a couple minutes, sorry about that, but I'll try to keep it brief. I'm sure nobody's interested in going to lunch anyway, right? So first of all, what do we know about PCGs? This is going to look very familiar to a slide that you'll see later in Peter's next talk, because indeed, this is using tools with homomorphic secret sharing. But roughly, let me kind of focus on a couple things. So first of all, in terms of these ones are really like theoretical results, but in terms of good concrete efficiency, there's a lot of really motivated stuff that you can do. And in fact, this Lapland region in here is getting better and better. And I think this is really a sweet spot, a very interesting regime for these constructions. And they're getting better and better. There's a lot of work going on from different groups that are having fantastic ideas building on top of this stuff. So Lapland, this is our goofy name for things based on LPN or LPN and friends. And this is something I want to draw your attention to, even if I don't get to kind of describe why. But at a techno level, so LPN ends up being really useful here, really useful and very efficient. And this is a bit odd for, maybe it was at least odd for me, is that in cryptography, we're just seeing fully homomorphic encryption, attribute-based encryption, all these important, amazing things that we know how to do from LWE, but not at all from LPN. And suddenly now there's a regime where this is a bit switched. I don't know how to achieve this kind of concrete efficiency at all from LWE. And it turns out being very targeted with LPN. And the reason is that somehow, so the difference between LWE and LPN, essentially both are okay. Here is LPN. So LPN is saying, suppose that I take a secret, I expand it out by a large public matrix. Okay. Of course, if I give you just lots of, if I give you that, you can tell that it's in that this doesn't look random at all. But if I add a little bit of noise, and for the case of LPN, this noise is very sparse. Okay. For the case of LWE, it's also little noise, but it's little in the sense of norm magnitude. So it's all over the place, but each of the values are very small. Versus here, it's only in a small number of positions, but the values in those positions are very large. It's a totally random element in those positions. Okay, and somehow the sparsity of this noise is something that we really are able to leverage using the necessary type of tools. Okay, so let me just quickly, I just want to give you a little bit of an idea. So trust me that this representation of LPN is actually equivalent to a different version, which we sometimes call a dual version, which is saying, okay, if I instead take a sparse noise vector and I compress it by a related public compressing linear matrix, that this kind of compressed string looks uniform. Okay, this is an equivalent version of LPN, where of course the two matrices are different but related. Okay, and this, so now even just describing exactly this, somehow viewing this LPN as a weird pseudorandom generator ends up being a useful interpretation. So what is the pseudorandom generator? Okay, so this it seems like I'm starting with something very long and I'm getting something random that's shorter. But recall that this long vector is sparse. So actually the description size of this long sparse vector is much smaller. I can view this as sort of the PRG seed. Then there's some deterministic way of expanding this to a corresponding sparse long vector and then compressing with the public matrix to get uniform. So this can be interpreted exactly as a PRG. Now, as a PRG, this is not great properties. For example, this step from here to here is like very high degree. This is not something you would want to really compute a lot. But it turns out this as a PRG is very friendly to homomorphic secret sharing, which I'll leave Peter to talk about. But just kind of, how is that the case? Okay, I'm just describing exactly the same function. So from seed to sparse noise compressed down, I'm describing this now horizontally. So this is the seed to the large sparse noise compressed down. So what are those two different parts? And note already that the second part, I said, is compressing by a public linear map. Okay, and this, hopefully I can already convince you, is something that's very friendly for computing on secret shares. Because if you have even just additive secret shares of some value, I can compute a linear function homomorphically on those additive secret shares just by computing it directly on the shares. And that gives you exactly the procedure that you need. Okay, so then the leftover part is, okay, so how do we deal with this weird compressed like seed down up expanding to sparse noise? And it turns out that in fact, in fact, what I wrote before, so actually it's more function secret sharing for point functions, gives you a way of doing that. And I won't be able to go into details of that, but either trust me or ask me about it, either in the break or whenever you see me around next. And I'll bust out all sorts of discussions on it. Okay, but the takeaway here of this part is just that this LPN structure, and here, the fact that this can be done cheaply, this part is crucial, the fact that this expansion is sparse. That's really like these point functions, you can think of this as going to be kind of a truth table. So for example, if the sparsity was just 1, this is exactly a truth table of a point function. The sparse noise is like 1 sparse, that's zero everywhere except for one value that's non-zero. So maybe this already gives you a little bit of a flavor of how these tools can be useful. Okay, I'll skip the concrete efficiency numbers, but take a look afterward if you're interested. The long story short is that this is the way that you should generate a lot of your correlations. So using some of these approaches, in particular for vector OLE and string OT, this is really in line. And for OLE, this is like a version of multiplication triples and triples indeed. Is very, very competitive. Okay, so and it has this, so not only is it like it has this useful property that you're doing the communication, by the way, is hands down like beating everything else. The non-silent alternatives, so we call this PCGs are like silent preprocessing because you have these small seeds and then most of the preprocessing complexity or a lot of the preprocessing complexity is this local computation that is silent or very quiet. You're not talking to people. So it's a trade-off of communication to additional computation, but now it's getting to the point that the runtimes are comparable anyway. So we get the comparable runtimes and much, much better communication. Okay, so to conclude, first of all, cryptographic correlations, super useful for secure computation. Very cool topics, lots of interesting questions. I described to you maybe two kind of high-level things. First of all, a description of what, a discussion, let's say, about different types of correlations. What are things that are useful? Take a look if you want as a reference afterward for a lot of examples. And this unifying framework based on function secret sharing. Then how to actually generate correlations. I gave an example of a protocol. In a lot of cases, kind of this recurring idea that weak versions of either fully homomorphic encryption or weak versions of homomorphic secret sharing could be very useful in aiding in generating correlations. And this notion of pseudorandom correlation generators. So where you start with short correlated seeds and you can locally expand these. And the punchline there, so there's a lot of active work and that there's a lot of very interesting stuff from learning parity with noise. Okay, let me just kind of leave up open questions and I'll be happy to take any questions if you guys have.
Elette, can you hear us if we just yell? Does this work?
Oh, I do. Yes, that's wonderful.
Any last questions before lunch?
Well, don't phrase it like that. Yeah.
Oh,
yeah.
The second half of your talk, Elette, is. No,
What was that?
Never mind.
Oh, yeah. Yeah, exactly. I have like 30 more,
Yeah. Well, all right, let's thank Elette again. We'll be back at 2 with the second half of Peter's talk. Thanks, Elette.